Hello, my name is Anirban Mukhopadhyay. I am a professor from Department of Computer Science and Engineering, University of Kolkata, India. I am going to present our research paper titled as an efficient implementation of iterative partial transcription for the traveling salesman problem. My co-authors are Professor Darrell Whitley from Colorado State University and Professor Renato Tinós from University of Sao Paulo, Brazil. The traveling salesman problem is a well-known optimization problem. Here we are given a weighted graph where the vertices represent the different cities and the edges between the vertices represent the direct paths between the cities with certain costs. Here the goal is to find the shortest possible tour that will start from a particular city and will traverse all the cities exactly once and come back to the originating city. So basically we are trying to find out the minimum cost Hamiltonian cycle. Traveling salesman problem has wide applications in the areas of vehicle routing problems or circuit layout problem or gene ordering problem in bioinformatics, etc. So computationally, the TSP is a hard problem. So this is an NP hard problem. Therefore, the different heuristic methods have been used like 2-opt or 3-opt local searches, which try to swap different edges in order to improve a particular tour locally. And there are more sophisticated local searches like Lean Kernighan Halsugan heuristic or LKH heuristic or edge assembly crossover genetic algorithms. So in LKH heuristics or in genetic algorithms, they generally try to combine two parent tours in order to generate some better solutions, better offspring solutions. So crossover or recombination is an important part of these heuristics. Over the years, the researchers have proposed different crossover operations for traveling salesman problem, and one of such popular crossover operation is called the partition crossover operation. Here, the approach is that given two parent tours, first we remove all the common edges from both the parents, and then we try to find out some disjoint partitions such that in each partition both the tours enter and exit from the same cities, but within the partition, although the set of same cities are the same, but these two parents follow different paths within the same partition while entering and exiting from the same city. So basically, these partitions represent some common subchains or some matching subchains starting and ending with the same city in from two parents. So once these have been identified, so these can be considered as the recombining components, and from each recombining component, we choose the shortest subtour from the either parent and then combine with the remaining part of the tours to get the corresponding offspring solutions. So partition crossover operations are uh, good and very popular because it can be proved that when they are applied on two parent tours which have been optimized locally by some local search operator, then the corresponding offspring solution that is found by a partition crossover operation is also locally optimal under the same operation. The iterative partial transcription is a partition crossover operation which has been used classically in the LKH heuristic. This iterative partial transcription works on the sequence representation of the parent tours and iteratively in a loop tries to find out all possible matching substrings of size between 4 to n by 2 in either direction. That means when there's both the parents are scanned in the same direction or they are scanned from two opposite directions. So therefore, the worst case time complexity of IPT is order of n square. So in this particular work, we have proposed an improvement in the implementation of the IPT. So our goal is to find the same recombining components that are found by the IPT, but in linear time. In the proposed approach, first we remove all the common edges from the two parent roots, and then we look for the vertices which have 4 degrees. That means there are no common edges associated with those vertices. So we split these vertices to create some ghost vertices like this, and just add a common edge with cost 0 between these two vertices. And then after doing this, definitely that all the nodes, all the vertices will have exactly 3 degrees. That means one edge will correspond to the red tool, one edge will correspond to the blue tool, and another edge will be the common. So this will be for all the vertices. So the same thing is done for when we scan both the parents in the same direction, and when we scan one of the parents, for example P1 in the forward direction and P2 in the reverse direction. So once we have inserted the ghost vertices in the tools, we keep track of for each vertex that out of these 3 possible edges, which edge is coming from the red tool, which edge is coming from the blue tool, and what is the common edge. That information has been kept here in a particular table, that for each vertex we keep track of that information, that what is the edge for each vertex. For example, vertex 1, what is the edge coming from P1, what is the edge coming from P2 in the, if we consider in the same direction, or what is the edge coming from P2 if we are considering the reverse direction of P1, and what is the common edge. So that information is kept for all the vertices, and these information, this part of the table, what we called as the extended edge table, this table can now be used to extract all the partitions of the uh, all the partitions from the union graph. Once we remove these common edges, when all the common edges are removed, this union graph is broken into partitions, which we call as AB cycles, because in these partitions all the nodes can be traversed alternatively by traversing the edges of two different tools, and so red blue and so on. So that's why they are called AB cycles, or red blue cycles, whatever you call it. And these AB cycles, among these AB cycles which have exactly 2 entry and exit points, which are we call as portals, so they will be called as recombining components. So they will be the recombining components, so they will represent the matching substrings from the two parent tools. But the other AB cycles which are not which cannot be immediately considered as the recombining component, because they have more than 2 portals. We find out all these AB cycles by just keep traversing these nodes alternatively from 2 different parents because of AB cycles, so red, blue, and so on. And then we just mark that which nodes go to which cycle, both in the forward direction and in the reverse direction. And then we also identify what are the portals. Portals are definitely those nodes whose common edges belong to the other, that leads to the other AB cycles. So just in the forward direction as well as in the reverse direction also, we find in the same way the AB cycles, and here you can see that there are 2 recombining components that we could have found, because in these 2 AB cycles we have exactly 2 portals. To look for the further recombining components, what we did that what recombining components that we already have got, we just communicate this information of portals from those recombining components to the other AB cycles which are not yet recombining components, and then the corresponding portals which have a common edge to the portals of a recombining components, they can disappear. Like here 12 and 7 get disappeared because they have common edge to 2 portals from a recombining component, and if we are remained with 2 portals exactly, then this cycle also becomes a recombining component. Another way of finding more recombining component is just merging 2 cycles, 2 or more cycles, if they have some more than one common edge, which corresponds to several portals, and uh, these portals get disappeared because they have common edges to other portals from other cycles. And if we are again remained with two portals, then the merged cycle also can be considered as a recombining component. Now, once all the recombining components have been identified, then we find out what is the shortest subtours from each of the recombining components and join them together and add the common edges that we removed earlier to get the corresponding offspring solutions. Now, EET based IPT that we proposed that take for all the operation like inserting ghost vertices or construction of the EET, traversing the EET for finding the AB cycles, merging the AB cycles. So all these require order of n time, and also it may be noted that we may need more than one mergings. So therefore, but we have restricted the number of possible merging to a maximum value. So although we had kept it 100 for our experiments, but not more than once or twice that merging could be done for all the experiments that we have done here. To compare the performance of the original IPT implementation and the proposed EET based IPT implementation, we have done some experiments on both random and benchmark TSP instances. So before recombination, during in our experiments before recombination, we have improved each parent tool by the two-opt optimization and identical subtours, that is the common edges from the parents removed. Now, this is the results for the random instances. We generated several random instances of different sizes starting from 100 to 10,000. So, and this is the for each instance also we have repeated our experiment, repeated the recombination several times, and this is the average recombination time for these two algorithms. That this red one shows the original IPT implementation and the blue one shows the EET based proposed EET based IPT implementation, and you can easily see that the red one has looks like a nonlinear. This increase is nonlinear with respect to the sizes of the problems, whereas our proposed algorithm, the time is increasing almost linear in the linear fashion. And when we apply the algorithms on some real data or some benchmark data from the TSPLIB library, what we got that we did several experiments, but here I have just shown a few of them for each problem. We have just shown the results of 5 trials, 5 recombinations of random tools. And what we found that for each case, for each and every case, that both the algorithms actually generate the same solution, same offspring solution. So basically they are finding the same recombining components. But importantly, our proposed approach is generating or doing these recombinations irrespective of the sizes. They are doing this recombination is lesser time than the original IPT implementation. And this difference is more clear when we increase the size of the problem. So you see that here I have shown 4 and another 4 are shown in this particular slide, that as we increase the size of the problem, then the difference between the time that's average recombination time over the 5 trials is much lesser by when we use the ET based IPT implementation than the original iterative version of the IPT. So in conclusion, I must say that we have proposed an ET based linear time implementation of IPT, and we also have proven and given an approximate proof that ET IPT, ET based IPT and the original IPT are identical under almost all normal conditions. And during the experiments also we have got that both the algorithms have produced the same results, same solutions, but ET based IPT is much quicker than the original iterative version of the IPT. However, it might happen that under some pathological conditions that ET-based IPT implementation may fail to mimic the original IPT. We have to do more experiments on more data sets and more larger data sets maybe then just to test it out. And also in future we have planned to just incorporate this ET-based IPT in the LKH heuristic to look into its performance. So that's all. At the end, I would like to acknowledge the Fulbright Nehru grant that I received to do this work during my stay at Colorado State University. And I would also like to thank my co-authors Darrell and Renato for their valuable inputs and discussions. Thank you.